9 in the PM, second try. Big shout out to my main man, Cornball Jones. Coming at you live down Albert Street. Corkscrew and Pluto and the boys back home. 7.6 rotations, rotational symmetry. My ball pony. Pony. Yeah, up there. Yeah. Anyways, I'm going to whiz through this because we've already talked about it. I want it recorded in case someone's watching from home. In this lesson, you're going to study a different kind of symmetry, different than line symmetry, which is mirror images. It's called rotational symmetry. And you will put the phone away, Chris. Yeah, please, twist it upside down. I don't want to see you using it. Rotational symmetry involves shapes coinciding with themselves after a rotation about a given point. We usually think of it as the center, but it doesn't necessarily. Oh, okay. And we're talking about these windmills, and I was just about to say, and Rami had already talked about some things. If I took this windmill here and I took a picture a second later when this wheel had just turned that much, would you really be able to tell the difference? The picture would be identical, right? If I took this shape and just twisted from here to here, that point would now be right here, right? This point would have been there, and they look the same. If I wait a few seconds, when this spins to here, right? So that will have spun here. It'll look the exact same too. These have rotational symmetry. And I think you can pretty easily see with this windmill here that it has 3 positions of symmetry, right? Whereas this one has 1, 2, 3, 4, 5, 6, 7, 8 positions that are identical, right? Okay, so how are they different? They rotate about a center. And as I just counted the 8 versus the 3, you could just say they have different numbers of windmill blades. Okay? So I'm waiting for you to jot that down. You're doing that. Nope, you can't. You gotta write it. I got all the power. Okay. What are we thinking? Got it? Not quite. Sorry. How are they different? Okay. I'm moving now. To which angle does a sail or blade rotate in one full rotation? How much? 360 degrees. That's a full circle. So jot that down. You need to know that a full circle is 360 degrees. Okay? And, okay, this is just a common question. It doesn't have to be exactly the same. But examples of other rotations that you might have seen. Merry-go-rounds. Actually, you don't see merry-go-rounds too much anymore. They're really dangerous with the ones that I had when I was a kid. But Ferris wheels, tops, car wheels, designer logos, all kinds of things though, right? Not just fan blades. Okay? So there's 1 or 2 ideas you can write down. I don't care if you list the whole thing. But I'm waiting for you. You definitely need that 360, and you've got to memorize 360 degrees is a full circle rotation. 360? No, that's why I said you don't have to, that's why I went through the answers. 1 or 2 things. Ferris wheels, so you can just put that. Now, second here, I really want you to watch this and we'll see. Because I think you get it. But this shows up pretty good on you. A tracing of this shape is rotated about its center. We draw a line segment to help identify the angle and shape turned through before it coincided with itself. So, watch this on the original here. Folks, I said watch. I need all eyes up here. Okay. So the first rotation, right? That's rotation 1. That's only 90 degrees. Do you guys get that? Then, and it's right on top of itself again. Then the 180 degree rotation. It's a little smidgen off. You get the idea where that came from. Rotation 2. A third one, and then back again, right? So you guys get the idea. We're back at this. The shape coincides with itself 4 times in one complete turn. So you count the last one, that was 360. You guys follow that? Yeah. That idea there. Yeah. Coincides with itself 4 times. A shape has rotational, we're on the next page. Rotational symmetry when it coincides with itself after a rotation of less than 360 about the center. If it doesn't have rotational symmetry, you could still spin it around once, 360, and be right back on itself. But we don't call that symmetry. Okay? It has to have more than one. Somewhere less than 360. The number of times the shape coincides with itself during the rotation of 360 is the order of rotation. So if it has rotational symmetry, it'll have it the minimum 2, because it'll come right back on itself. The one we did the example of was rotational symmetry 4. For each match, the shape rotates through 90. We say the angle of rotation is 90 degrees. That is, well, you had 4 positions, so you go 360 divide by 4 on a calculator, and you'll get the smallest angle to rotate. In general, for rotational symmetry in the big box, hey, what's up? In general, for rotational symmetry, the angle of rotational symmetry is just take 360 and divide by the order of rotation, like the number of positions you could have, okay? We'll practice this. A shape that requires a rotation of 360 to return to its original position doesn't have rotational symmetry. So we can't use order 1, okay? Now, look at the hexagons below and state the order of rotation. Now, does A have rotational symmetry? How many times? Yep, nope, maybe. Maybe I'll try this. Okay. 1, 2, 3. State the order of rotation. 3. I'm going to do that now. And the angle of rotational symmetry. So the order equals 3. And I make that spaced out of it. And then the angle. 360 divide by 3. Anyone happen to know? Okay. Do that. Now you know. That is one. You can use a calculator also. What about B? Does it have rotational symmetry? How many times? 2. Yeah. I'll show it just in case. 1. Back again. 2. That math you can do in your head, I hope. Order. 2. Oh. 2. Angle. I'm not even going to show 360 divided by 2. 180. That's the angle you have to spin until you get to the next position. How about, yeah, order equals 2, and then the angle symbol equals 180 degrees. Okay, then, C, does it have any symmetry? Zero rotation. It has linear symmetry, but we're not interested in that. And of course, I got some practice stuff there. Take a look at this. And there's a whole bunch of stuff. It's pretty self-explanatory. Rotational, not linear symmetry is what we're looking at here. I think you can go with a yes, no on these. Just whizzing through this real quickly. Now the first one. Guys, come on. So the first one, I know the board went off for a second here. You're looking for rotational. At a quick scan, what's the first letter of the alphabet with rotational symmetry? Well, O does, but it's not the first one. I does, it's not the first one. C doesn't. So what is it? H. If you go in the center of the H and think of that as the spoke or the center of the wheel, yeah. Well, yes, but I was just looking for the first one. So you guys go under there and put a yes under H, then yes under I, and then keep going. Okay. But then take a look at these ones here. Road signs that have rotational symmetry. If these didn't have pictures, they definitely have rotational symmetry. But you have to look for a symmetrical picture within that too. Some of them do, some of them don't. That's pretty simple. But then you get to this pentomino. A pentomino is 5 squares connected, but they have to be touching at least one of the edges. You see why those aren't pentominos? Complete edge. How many pentominos can you draw? Record them on square paper and stuff like this. Which ones have rotational symmetry? You don't have to go on to the other page. 7-pin polygons. Same kind of thing, you'll do that. And there's some dot paper for you to try that. Okay, so that's your task for the rest of this time. We'll take it. We work hard. We'll see about going to the basketball game tomorrow.